Right, let's call it. Okay, hello everybody. I'm James Munro. I've originally been a physicist, but for the last 13 years I've worked at Man Group, which is a large alternative asset manager. And for that reason, you need to know that opinions are my own, and none of this is investment advice. Okay. So I'm going to talk a bit about ArcticDB and OLAP. My take on OLAP. So what's the story here? I'll talk a bit about tech and math, but what's the OLAP story? So it's kind of my experience looking after and working on ArcticDB and talking to a lot of companies who are looking at a lot of data, a lot of time series, a lot of financial companies, and seeing a lot of kind of large infrastructure OLAP setups, and then trying to use that for data science. And I was a little bit surprised, and so I just sort of want to give my take on OLAP, what I think it means, because it's not used consistently, this term, but also why I don't think it's like optimal for what people are trying to do. And I really have no idea how this is going to land, so I'd love some feedback. So you may all agree with me, or you may all disagree with me, and that's fine. And then I'll also talk about ArcticDB and how it's a bit different to traditional OLAP setups. So I mentioned Man Group, large asset manager. What does that mean? It means we look after assets. We're an alternative asset manager, so that typically means we're trying to provide alpha, so we're trying to be a diverse investment, so not providing just market returns, but absolute returns. And a lot of it is very quant driven, and for me that's always been like data science driven, so people are taking in data, analysing it, using it to predict markets and the risk of markets. And we do that at scale, so we've got several hundred engineers and quants. We've been doing it for a long time. We trade a lot, so something like $7 trillion a year, depending on the vol of the markets. And all of that comes because data's changing and data's telling us how to, what positions are best to take. And we do a lot of that in the front office in Python. So we kind of grew up with Python as a data science language over the last decade or so. And we've really extracted a lot of value from things like PyData and the Python open source ecosystem. So I went down a bit of a rabbit hole thinking about OLAP and how to talk about this. I went into the sort of database taxonomy rabbit hole, and I realized there's no good database taxonomy, like categorizing things. I think it's worse than trying to categorize life. At least there's like lineage with life, and there's some lineage in the ideas of databases, right? Where they come from, and the technologies and the evolution of technology. But like in the end, databases just have different features and different optimizations, and they're like at various stages of their like life cycle. So this is my take on what OLAP is about and what my thought about it is. So am I talking about OLTP versus OLAP? So OLTP, transactional processing versus like online analytics. That's the normal thing you find when you say versus OLAP, when you Google versus OLAP. That's what it's all about. No, I'm not talking about that. So I'm not talking about whether you should be doing OLTP or OLAP. In fact, I don't really understand them as orthogonal. They are hard to optimize for both, but there are plenty of good databases that try and do real-time analytics. So am I talking about cubes? So this is the idea of like database warehouses or business intelligence or star schemas. My early engineering career, I was building star schemas, and I regret that. I didn't have a good experience doing that. And my experience of business intelligence tools is they have their place, but they're not particularly great for data science. But I'm not talking about cubes versus non-cubes, okay? I'm not talking about trying to store multi-dimensional data and do analytics on it in those kind of setups. So I'm just thinking about this idea that you're doing on-demand like analytics. So you basically need, you're cool for the results. You're not kind of like batching it, doing it ahead of time. So you're online, and also there's some sense in which you're like transferring the problem to something else. So you're writing SQL typically, right? And the code's going to execute on the server-side environment. So that's it. So you're giving someone else the problem of the analytics, and it's on demand, right? That's what I'm talking about. And so I'm talking about the trade-offs of doing the server-side analytics in some sort of infrastructure versus just doing local analytics, developing in your like Python environment. So here I'm talking about this kind of typical kind of database architecture. You've got storage, and then there's some sort of system for OLAP databases that will do the execution and planning of that execution, and then we'll give the data back to the user, and then you've got some sort of reasonably lightweight API for the user, which is good at understanding how to serialize the queries, how to tell the server what the problem is, and how to get the data back. And obviously this could be an incredibly large clustered system in the cloud, or it could be one server, it could be like a local server. But they're separate processes, right? So if you're shipping your analytics to run in a separate process, what are the trade-offs? And if you're trying to do this at scale, what are the trade-offs? So in OLAP, you've got some sort of shared database infrastructure. You might be paying someone else. You might be paying like AWS, or you might be paying your infrastructure team to support this, but you've got shared infra. If you're just doing the analytics locally, using all sorts of tools like pandas, you've got a very low infra setup. You're probably downloading data, right? And then you're doing your analytics locally. So you've got an extra online environment you have to worry about versus a single environment, right? And it may be a simplified environment online, maybe it's just about executing SQL, or it may be as complicated as a local environment. It may be like, that you could go and ship and run your machine learning in the cloud. So here in the OLAP space, you're normally running SQL, right? This is how most online analytics is done, and then so you've got this extra, somewhat limited language, and it has to be limited because you need a way that it could be optimized. You need a way that it could be translated into a well-structured environment where you've got schemas of tables and run on that without having to worry about the version of that environment or anything like that, without having to install packages. So you've got this kind of expression language that lets you do that, but it's limited as a result of that. And then OLAP, it can be fast, not that fast, is what I'll try and explain, but also at a cost. There's a real cost to running this kind of infrastructure if you're going to do that. And then versus what I'm calling, by the way, I didn't say this, but OFLAP is not a real term, I just made it up for this presentation. But if you're just downloading data and doing analytics locally, then I think that's a generally faster and cheaper approach for data science. So that's what this story is about, okay? So hopefully we're on the same page. And then the final bit of the explanation is, well, obviously there's actually kind of a few more steps if you do online processing, because you've got an intermediate. So you've got your plan that you're going to execute, right? You're going to read the data from the storage, but then you've got this intermediate problem where you have to actually inflate, deserialize, and run the calculation on the data, and then reserialize, and perhaps, depending on how you've optimized, recompress the data before you transmit it back to the user, because you're typically going across the network, you're going across some process boundaries. And so there's actually more steps if you do online analytics than if you're just trying to do it locally, because you can just download the data, deserialize, inflate it, and do your calculation. So I think there's an inherent advantage to doing this kind of offline compute. Now I wanted a real example rather than just talking abstract all the time. So I am picking on BigQuery, but only from a place of deep respect for BigQuery, because I have some experience with BigQuery, and it is, in my mind, it's fantastical SQL processing, and it's not the only thing in the market, obviously, but there are a lot of large infrastructure, enterprise level tools out there, and BigQuery is one of them, and it's fantastic at a lot of things, so that's where I'm starting this conversation from. And they've got an architecture which supports that. It's called Borg at Google, with this sort of compute side called Dremel, with layers of optimization and distribution before queries are executed against storage. And they've got an incredibly fast networking infrastructure for shipping stuff around from Jupyter and Colossus for storage. And they've been developing this thing for a long time, and it's crazy scale. They've just got petabytes and petabytes spare. They don't even give it away. It's crazy for a cost, of course. Right. So. And if you're using BigQuery, right, you're writing SQL, and you're shipping you've got all your data in the cloud, you're shipping your queries, and so here I just did an example for this presentation where I'm going to use some of the Wikipedia analytics which is available, where it's all of the hits on the Wikipedia sites, doing a group by, selecting out things where it matches Google, and listing the results, this is the page titles. And and then I've got on the right, because this is a Python conference, this is doing in Python, basically. I just inserted the SQL expression in read GPQ. It does behave a bit differently because it actually, for some reason, decides it is to batch up into 4 different queries. So somehow it overfills the first query or something. And then also, because of that, it doesn't actually sort correctly. So you have to separately do the sort in Python. It's actually not quite as fast. So what does this mean? What does this happen for the user, right, when you do this? Well, actually, this takes like 15 seconds or so, Google BigQuery, but that's impressive because that's like half a terabyte process. So it scanned a very large table to do this query. It's returned a couple of 100,000 rows, and then it's cost something, right? So it's like in the pure SQL case where it didn't have to do this batching, it was $2.59, and when it did the batching, it was like $3.06. So that's like the one level, that's amazing, right? It's gone. In fact, Google BigQuery can like pass terabytes per second if you let it, get up to speed. But the few 100,000 rows is that fast. Like if you compare to a traditional SQL database, getting a few 100,000 rows back is kind of fast. But in the modern world, it's not fast, right? 200,000 rows of data back to the user is not fast. So if you're not doing group bys, but you're doing filtering, then it's not a good download speed. If all you want to do is retrieve the data, this is not fast. And so, in fact, I'm being a bit unfair because BigQuery will give you a few 100,000 rows per second. Most of the time here is being spent on the scan. So that's one part of the argument. And also, actually, I think this is very expensive. So, because to do this kind of work, you don't need to spend that much. So that's the other part of the argument. And then, if you're limited like BigQuery, generally, you're limited to doing SQL on the server side, right? Then you're actually kind of limited to a whole bunch of stuff that is not data science, in my view. It's not complicated enough to count as data science. You're basically just doing kind of joins, pivots, groups, expressions. You're just manipulating the data. You're not doing the real work. And so, there's all sorts of things that we know in life, why we're in this profession, which is the realm of programming languages and kind of AI tools and what have you, statistical tools. And so that's what we're actually trying to do with analytics. And so when you're trying to leverage that into OLAP tools, OLAP databases, you're kind of wasting your time a lot of the time, in my view. So, and just to sort of double down on that point, like in my experience, which is done in the systematic quant space, so that's where you're doing very algorithmic trading. Then the problem is basically going from data to trade and understanding how well you're trading. And all of those things, right, like when we're dealing with the kind of modern data and like modern complexities of running assets, like that's all data science. So you're processing billions of ticks of market data. You could be using all sorts of alternative data sets like company reports, ESG data, like so environmental data, and things like this. And then you're doing work on that data using all sorts of methods. Right, none of this fits into like OLAP, right? You're doing machine learning, you're doing like proper statistics, and then you're doing a lot of kind of rather complicated analytics on all this. And so this is like, it's just like very little of this is served by OLAP databases, in my view. So in the end, what we actually need as data scientists working on time series data release is basically good filtering. So my argument is filtering and downloading, right? And so you want to do filtering before you download for obvious reasons. But beyond that, you're not getting a lot of value. And so here I've got on the left is like how like tick data might be stored. You've got like bid prices and ask prices, and really you're selecting out Apple and the quote prices between a date range. And typically also in this industry, you're kind of you want the whole time series. You're not like taking the first price of the day. You're taking the whole time series. So you're really just filtering and downloading. In the end, like whether you're filtering for assets, some factors, or models you've built, whatever it may be, you're basically selecting columns and selecting time ranges. Okay? And if you're doing that, then what should it cost and what should the performance be? So, like if you store your data in S3, say you wanted to download that same 190 gigabytes of data that was scanned in BigQuery, that's 40 cents. If you've got it stored in any way sensibly, right? So you're only putting out the columns you need for the kind of roughly the date ranges you need. Then you're talking about the 200,000 rows. is like 38 megabytes of data, so that's going to cost you almost nothing. And the reality is, like, the download speeds from S3 in any cloud, right, is 20 times what you're typically getting out of this OLAP infrastructure. And so the cost, I've not written this well, so apologies, but the cost here is at least 20 times cheaper, and the performance is at least 20 times better when you're just thinking about downloads. Okay, to try and just double down on that, I've got an example of like also just thinking about the way the users want the data. So at the top here, this is bond data, and it's kind of, this is like the normalized view at the top. So I've got dates on the left, and then I've got repeating dates because I've got like different bonds by the IDs, and I've got prices of the bonds. And I've got lots of measures. So this is kind of a normalized view of data. But if you're doing data science, right, you typically want to work with one measure at a time, and you might be doing, if you're working with like lots of factors or lots of assets, then you want to do this cross-sectionally. So typically, for the users, you want to, the people doing the work, that you actually want to generate these kind of cross-sectional views, and then like how it's presented here might not be how it's stored, but basically you're looking for columnar storage of a time series where the times are connected to each other, so the numbers are next to each other if they're next to each other in time, and then each of the columns are like close enough together that you can do work across them, like matrices of data, right? We're doing things like optimization and linear regressions. We need matrices of data, so that's what you want. And so in this example, right, there was actually like 430,000 historical bonds that we're doing analysis on, right? So really, if you can filter for this and download, you're going to be much more efficient and much more performant. Right, before I go into why ArcticDB is good at this, I thought I'd say we're not the only people who have been trying to work on like lower infrastructure solutions, which are kind of also good at kind of data science. And I could have made this list very long, but really I'm just trying to say that there's other people who are kind of working on a less like server infrastructure type solution to these problems, like in the vector DB space, there's like LanceDB, there's TileDB, which is great for like multi-dimensional array data. There's things that are very well known, like Delta Lake stuff, which I think is best here, if I'm trying to say is less server infrastructure, is actually best represented by Delta RS, which is the like client-side only version of reading data out of S3 in Delta Lake, and Iceberg, probably best presented by PyIceberg for reading stuff without server infrastructure. And then other things here, have a look if you're interested. ArcticDB really ends up being optimized for time series for doing this. And so the way, okay, so I'll get into ArcticDB a bit. The way ArcticDB kind of ends up being useful for users is, one, it's kind of all about being incredibly easy and familiar in Python, but supporting, downloading tables of data, time series of data, doing queries on the data, incredibly high performance for time series data, and that's come out of the use case of supporting like lots and lots of tick data and time series data in finance. And the scalability, so another like an advantage of trying not to have all this server infrastructure is you can get the scalability of your storage, not of your the database bottlenecks. And so I'll talk a bit about that. But basically, we're pretty good at scaling from one user to thousands, and the savings of not running that kind of thing as well. So just because we're using shared storage infrastructure, you're paying the cost of storage. You're not also paying for the cost of running this kind of online analytics processing engine. And the kind of things we're actually optimized for are the large data frames. So both like billions of rows, but also possibly 1 million columns. So very wide tables. Another important story for like financial data is like sparsity. So in tick data, you don't get every field updated all the time. But then actually in like even with like low frequency data, like daily data, you have things that don't exist sometime and do exist later. So like stocks, like they're born and then they die. So there's a sparsity problem you want to deal with nicely. And then I'll come into the implementation, but if you're like creating consistency over shared storage without server infrastructure for the database, then you need a way to do that, and we do that with like immutable data structures. And so that naturally gives us also a time travel feature. So we can go back to previous versions of the data seamlessly, and that's actually a really useful feature when you're doing data science, right? You can go back and see what's changed in the data and also in your outputs. So I've talked about this already, but this is what we're used to. I've got some database servers running, and I've got some storage. And then what does this mean? Well, that means you've got some lightweight API typically. You've got your database servers are managing things like security, the optimization, execution of queries, the ACID transactional element of it, indexing. And then somehow the capacity and resiliency of your database infrastructure is kind of like a distributed problem between the servers and the storage. And it may be the storage is on your servers, but typically nowadays that's also separated out from your servers. ArcticDB and some of the other things I mentioned can work in this other kind of mode, where you've just got shared storage, but the data structure's been carefully chosen here such that you can work on it in parallel, even if it's the same data. And so there's no kind of intermediate server layer. And then what happens is your concerns move around, right? So suddenly you're actually doing execution of your any analytics you're doing before you return it to Python in the client. You're deciding how to fetch the data and things like that in the client. You've got a problem around your ACID transactions, I'll come back to that, and then your security, capacity, resiliency is all done by the storage, right? Because now you're basically looking for decent storage that lets you download and filter data quickly. On the whole ACID side, so the one thing that's hard to introduce when you don't have like the job queue element here of a database infrastructure is this isolation. And that means that isolation is like the idea that that your queries are not interfering with each other, or your writes and your reads are not interfering with each other. So if a classic example is you're running a shopping basket, like Amazon shopping basket, and you need to know that when you put things in the shopping basket that you've got enough stock. And if two people put things into the shopping baskets and you don't have a consistent view of the database, then you run out of stock and you can't deliver the goods, right? So you need linearizability of your transactions to get that right. And that's a very hard thing to achieve when you don't have this job queue. But the reality is, in our experience, like, especially when you're doing data science, you don't need that. You're not asking for that. That's more like an OLTP problem, right? You're doing transactional processing. But here we're just like loading historical data and running models on it and doing predictions and things. And so you don't need this isolation. All you need to then figure out is that, okay, how am I updating that table consistently? And typically you can do that from a single process and never worry about isolation. So on the data structure side, I don't think any of this really should count as rocket science, but you're basically creating an immutable data structure, hierarchical data structure where you've got a data layer. So typically this would be an S3 where you're storing blocks of data, in our case tiles of those data frames. You've got an indexing layer which tells you what's in each of those tiles, and this would be a small object that you would load to decide what to download. And then because you need to update this consistently, right, you've got an atomic update process based on a kind of linked list of versions. So I add a new version, but the person reading version 5 can continue to read it, because version 5 is not modified. Version 6 becomes along. Any new reader gets version 6. So this is the kind of way we get consistency out of this. And the way you can filter the data without, by only having to load the chunks that you need. So what's happened for us is this was an internal technology. We had an earlier version that was open sourced, purely in Python. The new version is in C++, and we work with Bloomberg. We use some of their data. And so we talked to them about this, and they have this Python data science ecosystem called Quant, which they've been developing, and they were looking for a solution like ArcticDB, which was like almost infrastructure free, so they could deliver it to their users. And so we kind of came to an agreement that they could use ArcticDB, and that really kicked off for us ArcticDB as a business, a separate business. We're going to provide it to users. So that was a really great deal we made there with Bloomberg to get this whole ball rolling. And for them, they have ludicrous amounts of data, as you can imagine. So they're collecting something like 300 billion messages per day in terms of market data. And then they want to provide that kind of data to their users. So in the Quant, which is the product that the ArcticDB is deployed in, what they're doing is they're using that to provide things like futures data, all sorts of market prices, at scale to all of the users of the B-Core platform. And as I mentioned, this kind of kicked off ArcticDB as a separate business from Man Group. So there's a little team of us on London who are working on this, I should say London and Sofia in Bulgaria, so the people on the screen there. So far so good. So that's what that's about. And how are we doing for time? I've got a few minutes. So what I think I'll do is just do a very quick demo. Because what I've learned is demos like beat everything in terms of explaining how things work. So ArcticDB is truly like just client side. So I'm not going to connect to S3 here because I'm always worried about the internet. I'm going to do this locally, but all it is a Python package, which I happen to have already installed. So I'm going to import ArcticDB, and then just to kind of understand the structure of it. So you connect to some storage. I'm just going to use the disk here, and then you would have libraries. So these might be your data stores, might be your feature stores, but it could be your market data or some other database. And then tables are cheap. So you could have thousands of these libraries, and then you could have millions of tables. So they're kind of like cattle in this world. And you're just reading and writing tables of data. And you could have millions per library. And each of them is versioned. So if you're updating and appending to tables, you're just storing the diffs, and you can go back to previous versions. So I've got the very simple examples here. I'm going to use pandas to make a data frame of 1s, data frame of 2s, and a data frame of 3s. Okay. And then I'm just doing this locally. It's moaning about something, but let's see if it works. That's probably because I've run this notebook many times without restarting it. I've just got a sample library here, and I'm only going to read and write data frames. So here I've written that daily 1, which is the data frame of 1s, and I get a versioned item back. And it remembered the timestamp I saved it at. So you can use version numbers or timestamps to look up all the versions of the tables. And here it's like a string, right? This table's just got a name. But the idea is here, you can think of it like a key value store for tables, but it also understands tables. Yeah, or time series. So you could have a million different names for different tables. And I can read it back out again. And that was version 6. I can look at the data, there we go. So it's not just a key value store for objects, it's a key value store for tables. So I can append data, so I'll append the 2s, and then I can update data. So I can insert using the index, which is the date time there, insert the 3s, and I'll read that back out. So I've got the 1s, the 3s, and the 2s. But just to demonstrate bitemporality, or the versioning, and go back and read that original version, which I saved, which was like version 6 or something, and it was just the 1s. So it's all there. So that's kind of like the Noddy examples, but we can support very large tables. So here, I'm actually, for the sake, because I'm doing this locally rather than using S3, I'm just going to do 10,000 rows, 10,000 columns. So I'm going to create that using pandas, and then write that out. So I just wrote the table there, and then I can query the table out. So it's all very quick. Let's do extremely long but narrow table, right? So this is extremely long, so there's 100 million rows. It's not really that long, but it's on a laptop. But I'm going to read out 100 million rows. So that was very quick, right? And there we go, 100 million rows. See how fast that was. I struggled to do that correctly, I think. Let's try that again. I've made a mistake in my math somewhere. That's too fast, but that's too slow. But it was really very quickly. And then there's data to do queries. So there's actually a lazy data frame feature. This is just a way to build queries. We're big fans of Polars, and actually Polar support is coming soon, and I recommend using their lazy data frame kind of query language. But this is what we got in an attempt to model the pandas query approach. So here, reading out from that length, so this somehow I calculated this correctly here. So reading out in half a second and doing filtering for prices here, and that was 2 million. You can see the data's there. So that's what it looks like and feels like. And I think I've still got a few minutes before I need to sort of ask you if you've got any questions. So I'll just visit a few other points. So we've been working on the performance of this extremely hard. So this is, I'm afraid, not available in the latest version yet, but it's on a branch. But we've got something we call our V2 encoding, which is incredibly good at storing tick data. So we've got some simulated tick data here using random prices and volume, like integer volume numbers. And they're here reading it out of local SSD at over 1 billion rows a second. And then in terms of scalability, so this is, so we're used to running this in the cloud for people like Bloomberg, but also on premises for ourselves. So using the S3 servers on the right, we're like, we're often seeing, so this was last couple of months ago, but often seeing 50, 60 gigabytes per second from the storage, and what that's doing is that's people reading and writing out data to ArcticDB from thousands of Spark nodes. So we have a large Spark infrastructure, something like 20,000 cores, and so people are reading and writing data frames for that. Just to give you a sense of scale, it's several thousand like HD movies streaming at once. It's that kind of scale. So that's kind of the talk. OLAP is not for everything, and by OLAP I mean like large server-side infrastructure. It's not very good at data science in my view. I'd love to hear people's views on that. And there are people who are kind of trying to develop low infrastructure solutions, and I'm sure you've seen some of them at this conference, which offer other ways to just be good at downloading and filtering data and doing that fast and cheaply and easily. Thank you very much. Please check out ArcticDB.
We can take a couple of questions.
So no example of the time series going down in the columns being the Q-SIPs, and you held it at 100,000, right? The column, the number of columns.
Yeah.
Some of the challenges I'm facing a lot of times, new Q-SIPs show up, right? What do you do then?
So actually we have, one thing I didn't go into is ArcticDB is actually kind of schemaless. So when you're appending data, you can add new columns as you go. And if the column name matches, it will append to the existing columns. If it's not, it will create new columns. So that's what. So we've built features in for that.
Is it expensive in terms of like adding additional columns?
So what it does is it will. So you kind of have to just. When you load the data and you're including those columns, it will backfill like nans or zeros, depending on the type, for the history. So which is faster than downloading a made-up history. So so it doesn't really cost us a lot. What it ends up being is hard to implement.
Thanks.
All the examples showing the data that supports strings and categoricals?
Yes and yes. So by default, the strings are stored in a dictionary, so the categorical kind of fit is pretty good. That doesn't really help if all the strings are different. Where that's also changing. So we're about to release the arrow types support, so there will be support for the arrow string type.
Great presentation. I have two questions. I think the first question I have is like the ArcticDB as a storage support assistant. Like, how does it compare to like more commonly designed for like time series arcade? What is the shining points that's aside from just building time series? That's my first question. Like,
so I think you could think of ArcticDB like Parquet as far as the file format. Parquet incredibly well used, and it's pretty fast. It's definitely faster than getting things out of SQL databases. But we've spent a lot of time on performance of ArcticDB, so we are in general faster than Parquet. And as you kind of see, hopefully there's the whole database features over the top. So you're building data sets and feature stores and things, rather than just be a file format.
Does that limit you from using other tools like ArcticDB to query this?
Yes.
Okay.
In terms of roadmap, we're working hard to get our arrow support out, and so that gives us a lot of zero copy compatibility with DuckDB and Polars. And then Polar support, or direct Polar support, is going to come a little bit later.
My second question is related to the historical point in time, right? Because I think your storage system uses some time travel that's like for each. I actually don't know whether it's on the row level, the column level, and like version for each of this. But does that mean it's possible like variable storage on the device, and that will make like backfill or challenge that
So
your historical point in time, like does it how does it impact the backfill, etc.?
So as I mentioned, there's some schema-less kind of ness to ArcticDB. So you could add columns as you go, and it will backfill with like nan or null. The other option is obviously to just write new data for the whole table, and it doesn't have to match the schema, so you just replace the whole table. In terms of like how the way it's stored is it's tiled, so like groups of columns and groups of date types are stored together in blocks. And so if you're making new blocks which are not interfering with the existing blocks, then it kind of is pretty efficient.